Picture this. It's 4:55 p.m. on a Friday. You have your coat on.
Oh no, I know exactly where this is going.
Right. Your weekend plans are locked in, and you just need to do one last thing. You hit run on a routine daily pipeline just to, update the master historical database. The progress bar completes, you get the little green check mark on the canvas, and then your stomach just completely drops.
Yep, the realization.
You realize you just left the output tool on append instead of overwrite. You just double your company's historical revenue data in like 3 seconds flat. And reversing that mistake, that is going to take your entire weekend.
It is the absolute universal nightmare for anyone who handles data. I mean, the sheer panic of realizing you just corrupted the master record because you didn't check your gatekeepers.
Exactly. Welcome to this deep dive into the gatekeepers of data. Today, our mission is to demystify the 4 essential tools in Datok that control data ingress, egress, auditing, and active debugging. Because if you don't control the borders of your workflow, your entire pipeline is just, it's a liability waiting to happen.
Absolutely.
For you listening, my name is Alex Martinez, and I'm a veteran data architect. I've spent over a decade wrestling with complex Alteryx and Tableau pipelines, so I know the pain of a bad data gate all too well.
And I'm Sarah Chen. I'm a tech analyst and educator, and I absolutely love breaking down complex systems to see how they actually trick under the hood. Today, we're specifically looking at the in-out category of the prep module palette inside Datok.
Which brings me to a terrible data joke to set the mood.
Oh boy, let's hear it.
Why do data engineers make great nightclub bouncers?
I have no idea.
Because they always check your inputs and never let bad records through the gate.
Oh, wow. Okay, that is definitely groan-worthy, but it perfectly illustrates the concept. If you don't control the doors, the inside of the club is going to be an absolute disaster.
Exactly.
And for you listening, we need to set the architectural stage before we get into the specific tools. Datok is a 100% local offline application. It uses a visual node graph on a site-escape canvas to build your pipelines.
Right, so you're dragging these colorful tools onto a dark canvas, connecting them with edges, and visually building a flow.
Yep, but today we're ignoring all the complex transformations in the middle. We're just looking at the borders, the absolute beginning and the absolute end.
Right, because before you can join tables or pivot columns or parse strings, you have to actually get the data into the room. You have to open the front door. So we're starting at the very beginning with the input data tool.
The green node.
The bright green starting block. When you drop this tool onto the canvas, you configure it to point to an external file path on your local machine, and it pulls the data stream right into the environment.
And the sheer range of file formats supported by this single green node is what makes it so robust. You have your standard everyday CSVs, Excel spreadsheets, JSON files.
The usual suspect.
Exactly. But it also natively handles massive, complex formats like SQLite databases, Apache Parquet, and Apache Avro.
Okay, let's unpack this. Because as someone who has spent years in the corporate data trenches dealing with, insanely expensive software licenses, there is a specific feature of this green node that I completely geek out over.
Right, I think I know what you're going to say.
It's the native decoding. Datok has the native ability to decode proprietary Alteryx files, the .yxdb files and Tableau extracts, the .hyper files entirely locally. Let me emphasize that. You do not need an Alteryx server installation. You don't even need Tableau desktop open on your machine to read these files.
If we connect this to the bigger picture, it really represents a massive architectural shift in how we handle legacy data. Let's look at why that local native decoding actually matters so much.
So please do.
In a traditional modern data stack, if you want to migrate or transform a highly compressed, column-oriented extract like a .hyper file, what's the standard process?
Painful.
Yeah.
That is the standard process. I mean, I remember a project last year where we had a 40 gigabyte Tableau extract sitting on a shared drive. To do anything with it outside of the Tableau ecosystem, we had to upload that massive file to a cloud storage bucket.
Which takes forever.
Right, and then spin up a very expensive cloud compute instance just to decode it, translate the data, and then pull the flat results back down to our local machines. It took hours, and it cost real money just to get the data ready to be looked at.
Exactly. It's like you were forced to mail a foreign document to an embassy across the country just to get it translated and then, wait weeks for it to come back.
That's a great way to put it.
By having native decoding built into the local input tool, it's like having a bilingual speaker sitting right there in the room with you. Datok reads the binary data directly from your local documents folder, translates the metadata headers on the fly, and maps those proprietary types straight into scatol-compatible types.
Which is incredibly fast.
Blazingly fast. Because it relies purely on your local CPU and your disk's read and write speeds, skimming that massive cloud upload phase makes ingesting these heavy extracts so efficient. And crucially, it's completely private.
The privacy aspect is huge. I mean, your proprietary corporate data never leaves your hard drive. But speaking of heavy extracts, let's talk about the physical danger of pointing a green node at a file with, like, 50 million rows. If you just naively yank that into a web-based user interface, you are asking for trouble.
Oh, you're asking for a complete system crash?
Yeah.
This is where we have to talk about the underlying mechanics, specifically the JavaScript heap limit. When you're running a browser-based or an Electron-like local interface, the application only has a finite amount of active memory allocated to it by the operating system.
Right.
If you try to load 50 million rows into the active document object model, the DOM, or the browser's memory space all at once, you'll exhaust that heap limit instantly. The application will white screen and you'll lose all your unsaved work.
Been there, done that, bought the t-shirt. I once tried to load a deeply nested multi-gigabyte JSON file in a legacy tool and watched my entire system lock up so badly I had to hard reboot my laptop.
It's the worst feeling.
It really is. That's why the input data tools preview limit is such a vital localized safety net. Instead of loading the whole universe into the UI, it caches and lists just the initial rows in the preview grid.
Which saves your RAM.
Exactly. It strictly manages the memory overhead, so you can actually see your columns, check the data types, and start building your downstream pipeline without your computer fan sounding like a jet engine taking off.
It allows you to build the logic based on a sample, while trusting that the engine will process the full volume during the actual execution phase.
Right. So the green node gets the beta through the door safely, quickly, and without crashing your machine. But here's the thing. Just because the data is in the room does not mean it's good data.
Oh, definitely not.
You can't just blindly start piping it into complex joins and aggregations.
No, because real-world data is notoriously messy and unpredictable. You need to know exactly what you're dealing with before you start transforming it. You have to diagnose the patient before you operate.
Which brings us seamlessly to our second gatekeeper, the Browse Profile tool. If the input tool is the front door, the Browse tool is the dataset's nutritional label.
That is a perfect analogy. A nutritional label doesn't change the food inside the box. It just tells you exactly what you're about to consume so you can make informed decisions about your health.
Precisely. Because building out a massive 50-node transformation pipeline only to realize at the very end that your primary key column is missing half its values, that is soul-crushing.
Yeah, that's a bad day.
The Browse Profile tool sits right there on the site escape canvas and analyzes the data at that specific point in time. It gives you comprehensive table metrics, deep column profiles, and field null distributions.
Finding a high null rate is so common.
Oh yeah, finding a 99% null rate in what is supposed to be a quote-unquote critical business column using this tool, it's the data engineering equivalent of finding out your healthy green smoothie is actually 99% high fructose corn syrup.
This raises an important question about how we interact with data quality, and it really speaks to the workflow philosophy of Datok. The Browse tool is purely diagnostic. When you use it, you click on specific target fields within the tool's configuration panel, and it instantly generates statistical charts and distribution histograms right there in the interface. But, and this is key, it does absolutely zero cleaning.
Right. It doesn't replace the nulls with zeros. It doesn't trim the trailing white space.
Right. It requires you, the user, to apply critical thinking.
Yeah.
And this strict separation of diagnosis and treatment is vital for a clean architecture. The tool highlights the flaws like a massive unexpected spike in a null distribution histogram or, an age column where everyone is listed as 99 years old because it was a legacy default value.
Oh, I've seen that one so many times.
It surfaces that insight so that you can make an active decision about how to handle it downstream.
Cool.
Do you filter out those rows? Do you impute the missing values with an average? The Browse tool tells you what is wrong. You decide the cure using downstream transformation tools.
And just like the input tool, it has a built-in sample limit. Because again, we're dealing with local memory constraints. If you just want a quick profile of the first 10,000 rows to check for obvious anomalies, you can configure it to do that instantly without forcing the engine to scan a 20-gigabyte file.
It's very efficient.
It's a fantastic lightweight pit
Cool.
stop. But and there is a big but here. The Browse tool is a static snapshot. It's great for checking data at one specific physical stop in the pipeline. You wire it up to a node, you run the workflow, and you check the results. But data doesn't sit still. Once it starts cascading through a 50-node graph, that initial snapshot at the front door becomes obsolete pretty quickly.
It absolutely does. If a critical transaction record drops out at node 42 during a mismatched inner join, checking the front door doesn't help you find out where it went.
Exactly. You do not want to manually drag and wire up 50 different browse tools to every single step of the pipeline just to find one dropped record. You need a way to watch the data while it's moving. Which brings us to our third tool, and easily the most controversial one in my opinion, the monitor tool.
Controversial. I'd say it's arguably the most unique and powerful tool in the entire datok prep palette. It's a connectionless monitoring tool.
Okay, here's where it gets really interesting because I have to push back on this concept hard.
All right, let's hear it.
The entire mental model of a visual data pipeline, the whole reason we use a site escape canvas in the first place, is that you connect nodes with physical arrows to show the flow of data. Data goes out of one tool along an edge and into the next. If the monitor tool doesn't connect to anything, well, it's just floating there on the canvas.
Floating like magic.
Yeah, it feels like invisible magic. And historically, invisible magic in a pipeline is a documentation nightmare. How am I supposed to hand this workflow off to a junior developer if there are tools affecting the workspace that aren't wired into the logic?
I completely understand the hesitation. Invisible magic usually implies hidden dependencies, which are incredibly dangerous in engineering. But what's fascinating here is that the connectionless design of the monitor tool actually protects your mental model rather than breaking it, because it has zero impact on the business logic itself.
Okay, I'm listening. How does a floating, disconnected node protect the model?
Think about the traditional approach to debugging a missing record that you just mentioned. In other legacy platforms, you'd have to drop a filter tool or a browse tool after every single major transformation step and draw a physical line to it.
Yeah.
If you have a complex graph with multiple joins, unions, and aggregations, adding a physical tracker to every step means your canvas suddenly looks like a plate of spaghetti.
Yeah, it gets messy incredibly fast. You end up with 20 helper streams branching off the main flow.
And none of those helper streams are actually part of the ETL process. They're just there for you to debug. They clutter the visual space, making it much harder for that junior developer to understand the actual business logic of the pipeline. The monitor tool avoids this entirely by acting as a floating debugger.
Interesting.
When you drop it on the canvas, it watches and filters execution outputs in real time across all nodes simultaneously without you having to draw a single line.
It really is wild when you see it in action. For you listening, picture this. When you drag the monitor tool onto the canvas and activate it, it creates an active monitor tab at the very bottom of your screen. It sits right there, sandwiched between your results preview panel and your workflow messages panel.
And the mechanics of how it operates under the hood are brilliant. It
Yeah.
leverages the cached execution data of the local environment.
Yes, this is the part that I marvel at. You go into the monitor tool's configuration panel and you tell it what to look for. Say you're looking for a specific customer ID. It opens a little text box and you type in a substring value, maybe 12345. It's case insensitive, and instantly, without requiring you to run the entire pipeline again.
Which, depending on the data volume, could take minutes of processing time.
Exactly. Instantly, it reaches into the local SQLite cache and displays the matching records for every single active node in that bottom tab. You can literally click through your pipeline, node by node, and watch the exact moment where customer ID 12345 disappears because of a bad join condition. It saves hours of trial and error.
It fundamentally encourages rapid, iterative investigation. You're observing the state of the data across the entire ecosystem without permanently altering the workflow's architecture. And addressing your concern about handing it off to a junior developer when you're done investigating, you don't even have to delete it from the canvas.
That's true. It has a simple on-off toggle. When you disable it, the tool's icon on the canvas dims, a little red crossed-out circle indicator appears, and the monitoring completely suspends. It just sits there deactivated, leaving the business logic completely untouched until the next time you need it.
It's an observation deck, not a pipe.
It's like having a sophisticated security camera system for your pipeline. You turn it on when you need to find a specific guest who wandered off in the club, and you turn it off when the night is going smoothly.
Exactly.
Okay, so let's track where we are in our journey. We've checked the files at the door with the input tool. We've assessed their quality and null counts with the browse profile tool. We've tracked their movements through the complex joins using the connectionless monitor tool. Now the transformation is done. We have to close out the night. Which brings us right back to that Friday afternoon horror story I mentioned at the very top of the show. We arrive at the output data tool.
The output data tool is your purple target node. Once your data has safely flowed through the green input nodes and whatever blue transformation nodes you've built, it hits this purple node to be preserved. It exports the final processed stream back out of the datok environment and onto your local disk storage.
So what does this all mean for your actual files? It means you can write your final pristine data set out to a physical database or a flat file. You can output to .sclite, .db, .csv, or .parquet. But here's the critical part, the part that causes cold sweats for data professionals. This tool forces you to explicitly choose its write behavior in a drop-down menu. You must select either overwrite table or append rows.
And as we discussed earlier, mixing those two up can be disastrous for an organization.
It's a mistake you only make once. Appending when you should overwrite means silently duplicating data, inflating revenue numbers, and ruining downstream reporting dashboards. Overwriting when you should append means wiping out potentially years of carefully collected historical data with a single day's worth of records.
Just brutal.
But beyond simple user error, there's another massive risk at the point of output, which is system-level concurrency.
Yes, file collisions.
Right. Let's say you have a massive SQLite database powering a local dashboard. What happens if I have datok open in two different browser tabs? In tab A, I'm running a huge, long-running aggregation query against that master database to generate a report. But I forgot I left it running.
It happens all the time.
I jump over to tab B, I make a quick tweak to a totally different ETL pipeline, and I hit run. That pipeline finishes, and its output tool immediately tries to overwrite that exact same master database file while tab A is still actively reading it. In a lot of legacy systems, that collision causes catastrophic file corruption. You end up with a mangled, unreadable database that has to be restored from a backup.
Which is exactly why understanding the underlying mechanism of datok is so critical here. This is where datok's local architecture provides a massive, invisible safety net. Because datok operates natively on local SQLite file locks, it protects you from those concurrency errors at the operating system level.
How exactly does it handle the collision without breaking the file?
Well, all writes to these databases go through datok's local Python backend API. When your output tool in tab B tries to write to the file, the Python backend checks the SQLite locking mechanism. If tab A is currently reading or modifying that file, SQLite will have instantly placed a lock on it.
Makes sense.
The Python backend sees the lock, and instead of forcing the write and corrupting the file, it safely throws a database's locked error in your workflow messages panel.
The write simply fails.
Exactly. It fails gracefully, preventing data corruption entirely. It's a strict last write wins protocol, but it heavily guards the physical file integrity.
It's the bouncer stepping in at the end of the night and saying, hold on, the room is at capacity. Nobody else comes in until the current group is settled. It's a beautiful thing. You get a harmless error message instead of a resume-generating event.
If we synthesize what we've covered today, we're really looking at a masterclass in local border control. These four tools, input, browse, monitor, and output, act as the absolute gatekeepers of your environment. They dictate exactly what formats are allowed to enter, how their quality is audited before transformation begins, how they can be debugged on the fly without cluttering your workflow structure, and how they are safely and permanently preserved on your disk without corruption.
And for you, the listener, the main takeaway here is that mastering these four tools is the absolute foundation of becoming a datok power user. You cannot perform complex analytics, you cannot build sophisticated predictive models, and you certainly cannot train local AI on your data if you can't reliably control the flow of information at the gates. It's the unglamorous work that makes all the glamorous insights possible.
It's the absolute bedrock of data sovereignty and workflow stability. But before we wrap up, I want to leave you with a broader concept to ponder. We debated the monitor tool and its connectionless design quite a bit today. This actually represents a massive shift in how we think about data workflows as an industry. Historically, we've always treated data engineering like physical plumbing. You must rigidly connect pipe A to pipe B to see the water flow.
Right, the traditional linear pipeline. Everything has to be explicitly wired together. It just doesn't exist.
Exactly. But if we now have the local technology to observe data states instantly across an entire ecosystem without wiring up physical connections just by declaring what we're looking for, and letting the system check the cache? Are we moving toward a future where rigid linear pipelines are replaced entirely by ambient semantic observation, where the system just knows the state of the data everywhere, all at once, without us having to physically draw the map?
Man, that is a wild thought. Just floating intent over a sea of data instead of building the pipes with wrenches. It's definitely something for you to think about the next time you drop a node onto the site escape canvas. Just remember to check those IDs at the door, and for the love of everything, double check that pen dropped down on Friday afternoons. Thanks for joining us on this deep dive into the gatekeepers of Datok. We'll catch you on the next one.